When 3I Atlas split in deep space, astronomers expected the usual chaos: dust plumes, drifting shards, a cloud of debris. Instead, they saw nothing. The object separated silently, cleanly, and impossibly, leaving behind no dust trail, no fragments, not even a hint of disruption. A breakup without debris contradicts every model we have for how comets behave under stress. So what exactly tore 3I Atlas apart? An exotic form of ice? A burst of invisible gas? Or physics we haven't met yet? If mysteries like this make you question how little we understand about objects from beyond our solar system, don't forget to like and subscribe. Let's dive in. The separation of the comet took place far from the inner regions of the solar system, beyond the zone where sunlight still carries warmth, in a region where temperatures remain extremely low and changes unfold slowly. No spacecraft was present to witness the moment directly. No telescope captured an image of the instant when the body divided. There was no sudden flash, no visible outburst, no recorded surge in brightness that might signal a violent event. Across the darkness, the interstellar comet, known as 3I Atlas, divided into two bodies in complete silence. What followed was even more puzzling. The surrounding space showed no evidence of disruption. There was no cloud of dust expanding outward, no faint halo of debris reflecting sunlight, no trail of fine particles stretching behind the object. Instruments sensitive enough to detect extremely small amounts of material reported nothing unusual. The event left behind no visible scars in space. It was a separation without the usual signs of damage, a breakup without fragments, a physical change that seemed to contradict how fragile, icy bodies are expected to behave. At first, the anomaly appeared only as a subtle irregularity in the data. When astronomers analyzed the light curves, which track how an object's brightness changes over time, they noticed a shift that could not be explained by rotation alone. The signal suggested that something had changed in the structure of the object. Further analysis confirmed that the light was now coming from two sources instead of one. The comet had split, yet nothing around it reflected the chaos normally associated with such an event. Within the solar system, comet fragmentation is usually dramatic. As a comet approaches the sun, heat causes frozen gases to turn directly into vapor, a process known as sublimation. This gas escapes from the surface, dragging dust along with it and forming a glowing coma and tail. When a comet breaks apart, these processes intensify. Large amounts of dust and ice are released, producing expanding clouds, bright arcs, and long trails that can persist for weeks or months. These features are pushed outward by solar radiation and the flow of charged particles from the sun, creating visible structures that mark the event clearly. None of that appeared around 3I Atlas. The space around it remained clean. The absence of debris was not subtle, it was complete. For an object believed to be composed of ancient ice, mixed with rock and dust, shaped by long exposure to cold and radiation, such behavior was unexpected. The comet appeared to have separated with a level of precision that left no detectable residue behind. Silence, in this context, carries meaning. In observational science, the absence of an expected signal can be just as important as its presence. When familiar patterns fail to appear, it suggests that an underlying assumption may be incomplete or incorrect. Comets are among the most studied small bodies in astronomy. Their responses to heat, rotation, and gravitational stress are well documented. Their weaknesses are known. Their breakups usually follow recognizable patterns. 3I Atlas did not follow those patterns. The object behaved as if it were governed by internal properties or external influences that do not commonly apply to comets formed within the solar system. It separated into two distinct bodies, without the cascading release of fine material that normally accompanies structural failure. The event suggested control rather than collapse, separation rather than shattering. In this situation, the lack of debris becomes the most important feature of the observation. It acts as a signal, pointing toward an unfamiliar process. Fragmentation without fragments challenges basic expectations rooted in thermodynamics and material science. When stress exceeds structural strength, materials usually fail in a disorderly way. Cracks propagate, pieces break off, and energy is released through motion and heat. For an icy object with internal voids and volatile compounds, the expectation is even stronger. Yet here, that expectation was not met. This raises difficult questions. What does it mean for a comet to split cleanly? How could a body assembled under gentle conditions around another star, preserved for long periods at extremely low temperatures, divide without breaking down into smaller pieces? These questions push astronomy into areas where observation outpaces explanation. 3. I-Atlas originated outside the solar system. It formed around a different star, within a different chemical environment, under conditions that may differ significantly from those that shaped local comets. Its internal structure may reflect that origin: the ratios of ice to rock, the arrangement of layers, the presence of crystalline or amorphous ice, and the distribution of trapped gases could all differ from what is commonly observed nearby. As it entered the solar system, it carried with it information about a distant environment that cannot be sampled directly. When sunlight reached it, that information became briefly accessible. Observations during its passage offered a rare opportunity to study matter shaped beyond the sun's influence. Yet when the comet split, it revealed almost nothing about its interior. Normally, fragmentation exposes fresh material, allowing spectrometers to analyze dust and gas released from within. Each particle can carry chemical signatures, offering clues about temperature, history, radiation exposure, and formation processes. In this case, there were no particles to analyze. The comet revealed its change in structure without offering samples. It continued on its path, leaving behind uncertainty rather than data. There is a kind of restraint in such an event. The two resulting bodies moved along their trajectories smoothly, without signs of chaotic motion or rapid rotation changes. Their behavior suggested stability rather than stress-driven collapse. This stands in contrast to most observed comet breakups. Typically, fragmentation begins asymmetrically. One region weakens first, gas jets erupt unevenly, and rotational forces amplify the damage. The structure unravels, and dust spreads outward in complex patterns. Here, nothing unraveled. The separation appeared balanced, measured, and controlled. The rarity of interstellar objects makes this even more significant. Confirmed visitors from beyond the solar system are extremely uncommon. Before 3I Atlas, only one such object had been firmly identified, commonly referred to as 1I Oumuamua. That earlier visitor also behaved in unexpected ways. Its elongated shape, unusual rotation, and non-gravitational acceleration sparked long debates. Even years later, aspects of its nature remain uncertain. With only two confirmed examples, it is striking that both exhibited behavior unlike that of typical comets or asteroids formed locally. In such a small sample, anomalies dominate. This suggests that objects traveling between stars may not simply be familiar bodies displaced from distant systems. They may represent a broader diversity of structures and compositions than those seen near the Sun. The silent separation of 3I Atlas thus becomes more than an isolated curiosity. It points toward gaps in current understanding of how small bodies form and evolve in different stellar environments. In the vast spaces between stars, comets may develop internal features not commonly produced here. They may contain large internal cavities, layered ice phases, unusual gas distributions, or structural bonds shaped by radiation fields and temperature histories, unlike those near the Sun. Their pasts may include close passes by other stars, exposure to intense cosmic radiation, or interactions with environments that compress or alter material in unfamiliar ways. When such bodies finally experience stress, the results may not resemble familiar breakups. Instead, their histories may express themselves through behaviors that appear orderly but remain unexplained. Seen this way, the breakup of 3I Atlas marks the beginning of a deeper investigation. The absence of debris directs attention toward internal structure rather than external forces alone. It invites collaboration across fields, including astronomy, materials science, chemistry, and thermal physics. It challenges assumptions about the weakness of icy bodies and raises the possibility that some interstellar comets possess internal coherence beyond what is normally expected. As the two fragments continued their journey, the event served as a reminder that not every structural failure produces visible damage. Some separations are subtle, controlled, and precise. Such events act as puzzles embedded in observation, encouraging scientists to reconsider long-held ideas about what is possible. The silent division of 3I Atlas is one such puzzle. The separation itself is only the opening piece. The larger challenge lies in understanding the forces that allowed an ancient and seemingly fragile object to divide without leaving any trace of its undoing. The object was first identified not through dramatic discovery, but through routine survey work. Each night, automated telescopes scan large portions of the sky, comparing images taken minutes or hours apart to identify moving points of light in remote desert locations where dry air sharpens starlight and human activity is minimal. These surveys operate steadily and methodically. Within this steady process, 3I Atlas first appeared as a faint, moving point. It showed up consistently across multiple images, shifting position against the background stars. At the time, it seemed unremarkable. Its brightness was low, its motion steady. It was logged, catalogued, and passed through automated systems designed to calculate preliminary orbits. These systems quickly began to indicate something unusual. The object's trajectory did not fit the pattern of a body bound to the Sun. Early calculations suggested a hyperbolic path, meaning the object was moving too fast to be captured by solar gravity. Such results are treated cautiously at first. Measurement errors, short observation arcs, or noise can produce misleading solutions. As additional observations were added night after night, the uncertainty decreased. The calculated eccentricity, which measures how open or closed an orbit is, grew steadily beyond the threshold that separates bound orbits from passing trajectories. The conclusion became difficult to avoid. This object was not native to the solar system. It was passing through. Attention then turned to its physical nature. Changes in brightness and color suggested the presence of gas escaping from its surface. This behavior is typical of comets, especially those rich in volatile materials. Even at large distances, frozen gases such as carbon monoxide or carbon dioxide can begin to sublimate, producing detectable signatures. What stood out was how smooth and stable these emissions appeared. The activity followed expected trends as the object approached the Sun without sudden flares or irregular behavior. As more observatories contributed data, the picture became clearer. This was a comet, active and volatile, arriving from interstellar space. For many astronomers, the situation felt familiar. Only once before had humanity confirmed the passage of an object born beyond the solar system. That earlier visitor, known as 1I Oumuamua, arrived briefly and departed just as quickly, leaving behind more questions than answers. Its shape, motion, and subtle accelerations resisted clear interpretation, and years of analysis failed to produce a single explanation that satisfied every observation. With only 2 confirmed interstellar visitors on record, the pattern was difficult to ignore. Each arrival seemed to challenge established expectations, offering limited data and unresolved puzzles instead of clarity. 3I Atlas seemed to offer a different kind of opportunity. With its arrival, astronomers hoped to learn whether interstellar visitors followed shared patterns or whether each one represented a unique product of distant environments. There was cautious optimism. Unlike the earlier interstellar object, this body showed a visible coma, a surrounding envelope of gas responding to sunlight in ways that could be measured and tracked. Where 1I Oumuamua had provided very limited material for study, 3I Atlas appeared ready to offer more. Observations accumulated quickly. Astronomers monitored its light curves, tracking how its brightness increased as it moved closer to the Sun and began to warm. They watched the coma expand slowly, a diffuse halo forming as gas escaped from the surface. Measurements of its color index revealed subtle changes, small shifts that hinted at surface materials interacting with solar radiation. In many respects, it behaved like a familiar comet, an icy traveler awakening under solar heating according to patterns already well understood. Yet beneath this surface of normality, small inconsistencies began to appear. The rate at which the comet brightened did not match what models predicted for an object of its apparent size. The coma was present, but weaker than expected. Dust signatures, which are usually detectable even when a comet is far from the Sun, seemed muted. At the time, this did not trigger immediate concern. Comets are known to vary widely, and interstellar ones were expected to show even greater diversity. Still, the discrepancies were there, subtle but persistent. As weeks passed and the comet continued inward, observers prepared for a period when increased activity might clarify these irregularities. Spectral lines emerged from the gas surrounding the nucleus, allowing scientists to identify its composition. The signatures pointed to carbon-based molecules, icy compounds, and volatile substances typical of a cold body formed far from stellar heat. The overall picture remained consistent, with a dormant relic becoming active as it encountered sunlight. Then the pattern shifted. In a sequence of observations taken days apart, the comet's brightness stopped increasing as expected. Instead, it plateaued, then changed in a way consistent with elongation rather than simple brightening. Telescopes sensitive to fine detail began to detect slight distortions in the point spread pattern, the way the comet's light was distributed in images. These changes were small, but noticeable. They suggested that the object might be stretching, rotating unevenly, or possibly beginning to fracture. Additional observations were requested. Updates were issued through the Minor Planet Center, alerting observatories worldwide to focus attention on the faint interstellar visitor. When the new data arrived, it revealed what had been hidden within the earlier anomalies. The comet was no longer a single body. It had become 2. Even at this stage, expectations remained grounded in established experience. When comets fragment, they shed material. Dust and debris are released, forming trails and clouds that reflect sunlight and alter the comet's appearance. Fragmentation is usually loud in observational terms, leaving clear evidence behind. But the images showed none of this. Between the two emerging fragments was empty space, clean and undisturbed. The realization that 3I Atlas had split did not come from dramatic imagery. It emerged from careful measurement. Positions that should have aligned began to diverge slightly. What had once been a single point of light now behaved as two closely spaced sources following subtly different paths. The discovery was precise and mathematical, almost reluctant. A body that had traveled for ages between stars had divided, yet left no visible sign of the act. From that moment, the focus of investigation shifted. The question was no longer simply what 3I Atlas was, but how it had divided without producing a trail. The observational phase had been rich in data, but that data now pointed toward a contradiction at the heart of comet science. The realization unfolded gradually. It did not arrive through a single decisive image or a clear visual separation. Instead, it emerged through orbital calculations. Adjustments made to fit the comet's motion began to pull in opposing directions, as if two masses were influencing the solution. Initially, these discrepancies could be dismissed as noise or uncertainty. But when independent observatories reported the same deviations, the conclusion became unavoidable. The object had split. Such an event should have been unmistakable. Comet fragmentation is normally accompanied by violent release. Gas erupts from cracks. Ice turns directly into vapor. Dust billows outward, forming glowing arcs and halos under the influence of solar radiation. Breakups usually leave trails of lost material stretched along the comet's path, like fine grains scattered slowly through space. That was exactly what scientists expected to see. Instead, high-sensitivity images targeting the region between the fragments revealed nothing. No plume appeared, no dust halo expanded outward. The space separating the two bodies was darker and cleaner than the surrounding sky, almost stark in its emptiness. This absence directly contradicted established physical models. It was not simply unusual, it was deeply unsettling. The puzzle grew more intense when researchers examined brightness measurements. When a comet fragments, it typically becomes brighter. Fresh ice is exposed, internal material grinds and shifts, and volatile compounds are released, all of which increase light output. In this case, the opposite occurred. The comet dimmed slightly, as if the division had released no detectable energy at all. At that point, scientists began to consider that they might be observing a type of fragmentation never documented before. The standard mechanisms for comet breakup were each tested against the observations. Thermal stress should have produced dust. Rotational failure should have scattered debris outward. Tidal forces should have torn the body unevenly, accompanied by fan-shaped outflows. None of these signatures were present. The event began to resemble a paradox. If the comet had broken apart, something had either absorbed or prevented the processes that normally make such events visible. This left two broad possibilities. Either the breakup mechanism was fundamentally different from known cometary physics, or the fragments somehow avoided generating debris altogether. Accepting either option was difficult. Comets are considered fragile objects. They are made of loosely bound mixtures of ice, dust, organic compounds, and empty space. Their internal structure is thought to be porous and weak. Under stress, such bodies should crumble, not separate cleanly. A smooth division implies a level of internal coherence that comets are not expected to possess. The contradiction deepened when scientists compared estimates of the comet's mass before and after the split. The combined brightness of the two fragments did not perfectly match the original. This suggested that some mass had been lost. Yet no trace of that missing material could be found. If matter had been released, it must have taken a form invisible to instruments designed to detect dust and gas. A scientific riddle took shape. A comet appeared to have split without producing anything detectable from the act. This led to uncomfortable questions. Was the event truly a breakup, or could some other process mimic the appearance of fragmentation? Some considered whether two separate bodies might have been aligned along the line of sight and only later resolved, but their diverging paths argued against this. Others suggested the release of extremely fine gas phase material, but spectroscopic data showed no corresponding increase in gas emissions. Every alternative explanation weakened under closer inspection. The shock came not from what was seen, but from what was missing. Modern astronomy is built to extract information from faint signals. Telescopes can detect dust so thin it resembles smoke. They can sense gas emissions barely above background levels. They can trace trails dispersed across vast distances. Yet around 3I Atlas, nothing appeared. This forced a broader reassessment. Perhaps interstellar comets form under conditions that promote internal structures unlike those seen locally. They may develop cleaner planes of weakness or contain materials that fracture smoothly under stress. They may include substances that turn into gases too transparent or short-lived to detect. Whatever the cause, the event pushed comet science into unfamiliar territory. The universe is large and diverse. It may produce bodies whose behavior does not fit neatly within frameworks built from centuries of solar system observations. The response from the scientific community reflected this tension. Some researchers noted parallels with the strange behavior of 1I Oumuamua, pointing out that both interstellar visitors resisted standard explanations. Others urged caution, emphasizing that without more detailed data, firm conclusions could not yet be drawn. Even the most careful voices acknowledged the strangeness. Fragmentation without debris is not just rare. It undermines the usual methods scientists rely on to reconstruct such events. Without dust trails, composition cannot be sampled, grain sizes cannot be measured, jet directions cannot be inferred. Even the timing of the split remains uncertain, estimated only from the gradual divergence of the fragments' paths. The event existed only as a quiet imprint in the data, a change in motion revealed through calculation rather than sight. There was no physical evidence to accompany the conclusion, none of the visible markers that usually anchor such interpretations. It was as if the comet had concealed the moment of its own division, leaving behind only mathematical traces. The realization did not bring excitement or celebration. Instead, it brought a subdued confrontation with something that did not fit. Scientists were faced with two fragments where only one should have existed, separated in a way that resisted every known explanation. Independent observatories confirmed the finding, removing any doubt that the split had occurred. Yet confirmation did not bring clarity. The universe had allowed a form of fragmentation whose subtlety exposed the limits of current understanding. This was not simply an unexpected case. It challenged a foundational assumption that comet breakups must announce themselves through observable signatures. Researchers were forced to imagine mechanisms that were quiet rather than violent, precise rather than chaotic, operating at the edge between physical process and apparent absence. In the tension between the expected disorder of fragmentation and the calm emptiness that followed lay the core of the mystery. 3I Atlas had refused to follow the pattern written by dust, rupture, and debris. This behavior opened an unsettling possibility. Objects traveling through the vast space between stars may fracture in ways that science, shaped largely by solar system experience, has never encountered. The realization sent a ripple through the research community and set the stage for a deeper investigation into the true nature of interstellar matter. The laws that describe comet breakup are not loosely defined ideas. They are grounded in centuries of observation and in thermodynamic principles that describe how fragile celestial bodies respond to stress. In familiar cases, sunlight heats a comet's surface unevenly. These temperature differences create cracks. Frozen gases trapped within the body turn directly into vapor, forcing their way out through fractures and carrying dust along with them. Rotation increases strain, slowly winding the structure tighter until it can no longer hold together. Gravitational tides tear objects apart when they pass too close to massive bodies. In every scenario, fragmentation leaves clear fingerprints. Dust flows outward. Debris spreads along the orbit. Brightness changes abruptly. 3I Atlas followed none of these patterns. From the moment the split was inferred, scientists were confronted with a troubling contradiction. The event did not align with the physics meant to describe it. What made this more unsettling was the comet's calm behavior before the separation. Inbound comets often show signs of instability. Jets appear on one side. Brightness fluctuates. Activity becomes uneven as different regions heat at different rates. These behaviors are warning signs, precursors to structural failure. 3I Atlas showed none of them. Its coma expanded smoothly and evenly. Its brightening curve evolved in a controlled, predictable way. There were no sudden bursts of gas, no flickering changes, no hints of internal stress reaching the surface. Thermal stress, the most common cause of comet breakup, seemed inconsistent with such uniformity. For heat-driven fracture to occur, temperature differences must propagate cracks through the interior. Those cracks release dust well before a full separation occurs. Particle by particle, material escapes into the coma, forming halos visible even from great distances. Yet in every image taken before the split, the coma remained thin and subdued. It was present, but restrained. If thermal stress existed, it left no outward trace. Another possible explanation lay in rotation. A comet can spin faster over time until centrifugal forces exceed the strength of its structure. But rotational breakup is rarely subtle. It throws fragments outward, produces dust fans aligned with the spin axis, and often causes sudden brightening as fresh ice is exposed and begins to sublimate. None of these effects were seen. The separation of 3I Atlas appeared almost deliberate, more like a controlled division than a catastrophic failure. Tidal disruption offered another avenue, but the physics again resisted. Tidal forces strong enough to tear a comet apart require close encounters with massive bodies, such as planets or the Sun itself. 3I Atlas experienced no such encounter. Its orbit kept it safely distant from any region where gravitational forces could overwhelm its structure. It moved steadily inward, encountering nothing capable of pulling it apart. Internal pressure from volatile materials was also considered. Interstellar comets might contain exotic ices, substances that remain frozen at extremely low temperatures and then expand rapidly when heated. In theory, the sudden expansion of such materials could rupture a nucleus, but this process would still leave evidence. Gas emissions would spike, dust would be released, shock signatures would spread outward. Instead, the coma of 3I Atlas remained weak and undisturbed. The deeper scientists looked, the clearer the contradiction became. The comet's behavior before during, and after the split violated the frameworks used to explain all known fragmentation events. This was not merely unusual, it was destabilizing. It suggested that assumptions about cometary cohesion, about how these bodies hold together and how they fail, may not apply universally. For decades, models have been built on observations of solar system comets. These objects are generally thought to be fragile aggregates, loosely bound mixtures of ice, dust, and organic material. 3I Atlas appeared to possess a different internal architecture, one that allowed it to divide cleanly without shedding debris. This implied a degree of internal coherence unexpected in such ancient and porous bodies. One possibility was that the comet contained a pre-existing plane of weakness, a structural seam along which separation required little energy. Such a feature could arise through layered accretion during formation, a primordial fracture sealed by long exposure to cold, or a boundary created by slow thermal evolution around a distant star. Even so, tearing along such a plane should still produce dust as material separates. The complete absence of dust pointed towards something more unusual. Either the material along the separation plane was extraordinarily uniform, allowing a nearly frictionless division, or the comet possessed physical properties that actively prevented the release of particles. The latter idea pushed well beyond familiar intuition. For a body composed of brittle ices and loosely bound grains to separate without shedding fragments, its internal matrix would need to behave in unfamiliar ways. Some researchers considered whether long exposure to cosmic radiation might have altered the comet's chemistry, strengthening certain regions while weakening others. Others wondered whether internal voids might have collapsed silently, absorbing the energy of separation without ejecting material. There were even suggestions that dense, cohesive layers could exist within the nucleus, formed under pressures or conditions rarely encountered in the solar system. Each idea stretched existing models and highlighted how little is truly known about the internal geology of interstellar bodies. What became increasingly clear was that solar system comets may represent only one branch of a much broader family. The rules that govern their behavior may not apply across the galaxy. Objects formed around other stars, within different nebulae or cold molecular clouds, may follow different paths of evolution. Their responses to stress, heat, and motion may reflect conditions unfamiliar to Earth-based science. For researchers, this realization was both exciting and unsettling. Long-held principles were no longer secure. The assumption that fragmentation must be violent, that breakup must produce dust, that fragile structures cannot fail quietly, all of these ideas were called into question. The behavior of 3I Atlas suggested the existence of a different class of cometary objects, shaped by distant environments and governed by properties not yet fully understood. The response within the scientific community reflected this tension. New studies began circulating, proposing mechanisms that could allow a comet to split without visible evidence. Some focused on deeply buried volatile reservoirs that might vent in ways difficult to detect. Others explored materials with unusual sublimation behavior that would not form traditional dust trails. Still others examined mechanical failure modes involving internal grain bonding absent in local comets. Underlying all of these efforts was an unspoken recognition that established rules were bending. 3I Atlas had not behaved as comets are expected to behave. In breaking that expectation, it exposed a deeper fracture, not in its icy body, but in the assumptions guiding comet science. Each attempt to reconcile the event with known principles revealed further tension. The phenomenon stood at the boundary between the familiar and the unknown, Its quiet nature acted as a challenge to models that once seemed complete. The lack of debris, the calm evolution of the fragments, and the absence of diagnostic signals combined into a single conclusion. The event could not be explained without expanding existing frameworks. As the investigation deepened, attention turned once more to the empty space between the fragments. That gap grew in significance, less a physical separation than an intellectual one. In typical breakups, the region between fragments becomes a stage filled with information. Dust scatters light, gas emits across multiple wavelengths. Fine debris traces arcs and filaments through space. In the aftermath of the separation, attention shifted to the space between the two bodies. In most comet breakups, this region becomes dense with information. Dust particles scatter sunlight. Gas molecules emit across multiple wavelengths. Fine debris traces faint arcs that reveal the mechanics of the rupture. For 3I Atlas, this expectation guided the next phase of observation. High-resolution imaging campaigns were initiated, and telescopes equipped with extremely sensitive detectors were directed toward the region separating the fragments. Observers searched not only for large pieces, but for any trace of material at all: fine dust grains, microscopic ice crystals, or particles small enough to sit just above the background noise. Even the faintest scattering of sunlight would have been enough to indicate the presence of debris. What appeared in the data was not evidence of debris, but a kind of structured emptiness. Images from multiple observatories showed a clear separation between two faint bodies, divided by a region that contained nothing detectable. The boundary between them was sharp and consistent, not blurred by dust or gas. This was not the result of a single failed observation. The same absence appeared across different instruments, wavelengths, and observing nights. Optical telescopes detected no scattered light. Infrared surveys found no excess heat that might point to residual dust. Polarization measurements, which are sensitive to extremely fine grains that may escape direct imaging, showed no deviation from background levels. The empty region was not an artifact of technique or sensitivity. It was a real feature of the event. Astronomers then turned to the photometric evolution of the fragments. If material had been released, even briefly, the combined brightness should have shown irregularities, small fluctuations, sudden increases, or departures from smooth trends would be expected if new surfaces were exposed or if fine material dispersed into space. Instead, the light curves of both fragments remained remarkably steady. Their brightness followed smooth, predictable paths. This suggested that the separation did not significantly increase the active surface area, or that any newly exposed ice behaved no differently than the surfaces already present. Some researchers considered whether debris might have dispersed too quickly or been too fine to detect. One idea was that particles could have vaporized into gas almost immediately, becoming too faint to measure. Another was that dust might have spread into such low densities that it blended into the background of the solar environment. But these explanations failed to account for the full picture. If mass had been lost, it should have left a trace somewhere. Changes in thermal emission, increases in coma density, or alterations in tail structure would have been expected. None were observed. The coma around each fragment continued to evolve in a restrained and consistent way. Its size and brightness changed slowly, following trends associated with gentle sublimation rather than disruption. This behavior was difficult to reconcile with any known form of cometary fragmentation. As observations continued, the two bodies moved farther apart, and their separation could be measured with increasing accuracy. Their motion showed no signs of turbulence. There were no erratic deviations or sudden accelerations. Instead, They drifted apart smoothly, as if guided by a minimal and carefully balanced force. This calm divergence suggested that the separation involved very little energy. Whatever occurred inside the nucleus must have applied only a slight impulse to the fragments. Spectroscopic data supported this view. Spectroscopy breaks incoming light into its component wavelengths, revealing the presence and abundance of specific molecules. If sublimation had increased after the split, the spectral lines associated with common cometary volatiles, such as water vapor, cyanide, and carbon-based compounds, should have grown stronger. They did not. The spectra before and after the separation were nearly identical. Chemically, the event appeared silent. One by one, the usual indicators of cometary breakup were absent. There was no uneven outgassing, no emergence of new jets, no widening of the tail caused by released debris. The comet behaved as though it had simply transitioned from one body to two without disturbance. A pattern unlike any previously recorded began to take shape. The orbital behavior of the fragments reinforced this impression. Their paths diverged slightly, as expected after separation, but remained unusually stable. The relative speed at which they moved away from one another was modest, far lower than typical values measured in fragmentation events, driven by pressure buildup or rapid rotation. Instead of being pushed apart violently, the fragments drifted as if gently released. Such stability is rare. In most breakups, fragments inherit irregular motion from the parent body. They tumble, interact with escaping gas, and often continue shedding material. Their trajectories show complexity and disorder. The fragments of 3I Atlas showed none of this. Their motion suggested a shared internal history and a nearly symmetrical division, as if the nucleus had separated along a balanced internal boundary. This idea drew interest. If the comet contained a natural plane of separation, it could explain the smoothness of the event. However, even an idealized internal boundary should not be perfectly clean. On microscopic scales, material should flake away, dust grains should scatter, heat should act on freshly exposed ice. The complete lack of such effects remained difficult to explain. The stability of the fragments also hinted at a level of internal uniformity not commonly associated with comets. Solar system comets are typically heterogeneous. They contain regions of varying density, mixtures of dust and ice, pockets of volatile material, and voids. These internal differences lead to uneven forces during breakup, producing irregular motion. The clean post-separation behavior of 3I Atlas implied a more homogeneous structure. Such uniformity is rarely seen outside controlled laboratory conditions. Natural bodies formed in turbulent environments are expected to show irregular internal makeup. Yet, the data suggested that 3I Atlas may have been structured in a more orderly way. Each new measurement strengthened this impression. If the comet was uniform enough to split cleanly, stable enough to drift without tumbling, and quiet enough to produce no debris, then it likely represented a type of object not yet documented. Its interstellar origin became increasingly important. Long exposure to cosmic radiation over millions of years could have altered its internal materials, gradually changing the way grains bonded together. Alternatively, the environment in which it formed may have been fundamentally different from the region that produced solar system comets. It may have originated in a cold molecular cloud or around a star with different elemental ratios, producing ices with unusual mechanical properties. These materials might fracture smoothly rather than crumble, regardless of the cause. The absence of material in the wake of 3I Atlas became a defining feature of the event. Scientists were forced to focus not on what they could measure, but on what was missing. The empty region between the fragments resisted interpretation. Where dust was expected, there was nothing. Where disorder was expected, there was symmetry. The gap itself became the most informative aspect of the breakup, pointing toward processes operating deep within the nucleus. As the fragments continued to separate, their motions settled into a pattern that troubled even cautious analysts. Despite the emptiness between them, the two bodies behaved with a shared coherence. Their paths suggested a relationship established long before they entered the solar system. The kinematic pattern differed sharply from known disrupted comets. Instead of abrupt changes and scattered trajectories, the fragments moved along smooth, nearly parallel paths. This stability became a defining characteristic of the event. In most breakups, fragments inherit complex rotational states. Uneven mass distribution and asymmetric outgassing introduce chaotic motion. None of these features were present here. The fragments of 3I Atlas exhibited minimal differential rotation. Their angular momentum appeared to have been divided evenly, a situation rarely seen in natural separations. Orbital analysis made the anomaly clearer. The separation velocity, the rate at which the fragments drifted apart, was exceptionally low. Typical disruptions involve higher speeds because the forces involved act suddenly. Here, the speed was not only small, but consistent. It resembled the slow divergence of components that had been held together gently, or perhaps too perfectly, until a minor internal change allowed separation. As orbital solutions were refined over days and weeks, the consistency persisted. The data suggested that the breakup was nearly symmetrical, with little lateral force applied at the moment of division. There was no sign of thrust or recoil. Instead, the separation looked like a balanced release. This led some researchers to consider whether the comet possessed an internal structure more ordered than expected. One possibility was a layered or crystalline arrangement of ice. While no solar system comet has shown such architecture, interstellar environments could allow slow, ordered deposition of material. Over long timescales, cosmic radiation may promote gradual rearrangement of molecular bonds, strengthening some regions while weakening others. If 3I Atlas contained such layered structures, it might have separated along a boundary where the internal arrangement became unstable. This could produce a division requiring little energy and releasing almost no debris. Spectroscopic measurements offered limited but suggestive support. The chemical signatures of both fragments were closely matched. Their volatile compositions were nearly identical. Solar system comets often show compositional gradients. Different regions contain different mixtures of dust and ice, leading to varied activity patterns. In contrast, the similarity between the fragments of 3I Atlas implied an even distribution of materials throughout the nucleus. This uniformity extended to their brightness behavior. The light curves of both fragments tracked closely over time, as if their surfaces responded in the same way to solar heating. Such parallel behavior is uncommon in known comets, where irregular shapes and compositions produce more complex patterns. The coma behavior reinforced this view. After fragmentation, one would normally expect changes in shape and extent as new active regions develop. Instead, the coma around each fragment remained narrow and faint. There were no sudden expansions or transient jets. The rate of gas release appeared controlled and steady. This suggested that the breakup had not disrupted the internal network of channels that regulate gas flow. Some researchers began to consider whether the separation occurred gradually rather than abruptly. Instead of a sudden rupture driven by explosive forces, the nucleus may have relaxed slowly along an internal boundary. In such a scenario, the binding strength would decline until separation occurred quietly, without friction, and without releasing dust. If so, The breakup of 3I Atlas was not an explosion or a collapse, but a silent transition, a division guided by symmetry and internal structure rather than violence, leaving behind no debris and challenging long-standing assumptions about how comets, especially those from beyond the solar system, are built and how they fail. Such behavior has no known counterpart among comets formed within the solar system. Here, small icy bodies are shaped by relatively similar conditions: gradual warming, repeated solar passes, and radiation environments that have been studied for generations. In contrast, objects drifting through interstellar space experience extremes that differ profoundly. They endure deep and persistent cold, prolonged exposure to high-energy cosmic radiation, and possible interactions with molecular cloud chemistry. Over immense spans of time, these influences can reshape internal structures in subtle ways. Stresses may accumulate slowly rather than abruptly. Certain materials may anneal, becoming more ordered and cohesive. Volatile compounds may migrate and redistribute internally, settling into configurations that behave unlike anything familiar from local comets. Together, these processes could give rise to behavior that lacks the sudden violence usually associated with fragmentation. As the two fragments continued along their paths, astronomers tracked tiny deviations in their motion with extreme sensitivity. These measurements offered another important clue. The small differences in trajectory suggested that each fragment carried a slightly different mass distribution, yet not enough to indicate a chaotic or forceful separation. Instead, the divergence was gentle. It matched what might be expected if a single cohesive nucleus had divided into two nearly equal portions, each retaining sufficient structural integrity to travel independently without further disintegration. This soft divergence reinforced the unprecedented nature of the event. The separation appeared guided not by violence, but by an internal balance shaped by properties unseen in comets formed near the Sun. In this sense, the motion itself became a message. The geometry traced by the fragments hinted at origins far beyond familiar environments, at materials unfamiliar, and at formation histories beyond the reach of current models. With every hour of drift, the fragments told a story unlike any recorded before, urging scientists to look beyond the well-worn physics of rupture and toward the possibility that the galaxy contains bodies shaped by rules not yet fully imagined. As researchers reconstructed the sequence of events, one discrepancy overshadowed every explanation. The comet had clearly lost mass, yet none of that missing material appeared anywhere in the observations. The fragments were smaller than the original nucleus. Photometric analysis, which translates brightness into approximate surface area, revealed a measurable shortfall between what the comet had been and what it had become. This deficit could not be dismissed as error or uncertainty. It was written directly into the light curves. Something had vanished. In the familiar behavior of comets, missing mass almost always reveals itself as dust. Often this material consists of extremely fine grains rather than large fragments. Such particles drift into the wake, scattering sunlight and creating faint but detectable features. Dust clouds linger. They glow softly. They leave trails that persist long after the breakup. They provide information. Yet, 3I Atlas left none of these signs. Its wake remained clean and quiet. There was no brightening of the coma, no increase in scattered light, no thermal glow from heated dust, no polarization signature. The absence was complete. This forced scientists to reassess the breakup with renewed skepticism. If mass had been lost, but no debris detected, then the missing material must have escaped in a form invisible to standard observational tools. Several possibilities were considered, each challenging in its own way. One early idea was that the missing mass vaporized almost instantly into gas, too sparse to detect. However, such vaporization would require an enormous energy input. Interstellar comets, hardened by long exposure to extreme cold, do not typically respond to sunlight with rapid, large-scale sublimation. Converting a substantial amount of solid material directly into gas without passing through detectable intermediate stages would demand energy far beyond what was available. Moreover, even a brief release of gas should have produced temporary enhancements in spectral lines associated with common volatiles. Sensitive instruments detected no such spikes. Another proposal suggested that the material dispersed into particles so small, on the scale of nanometers or molecular clusters, that they became effectively invisible, merging with the solar wind. Yet even such ultrafine dust should have altered the background scattering profile slightly. Observations showed no such effect. The space around the fragments remained smooth and undisturbed. This led to more radical ideas. Perhaps the missing mass had been trapped within the interior until the moment of separation, then released not as debris, but as a short-lived, coherent outflow of gas. In this model, an internal reservoir could have vented quietly during the breakup, dissipating rapidly into space. But this scenario struggled against thermodynamic limits. Reservoirs large enough to hold significant mass would likely leave thermal or structural signatures before release. No such signs were observed. The problem grew sharper as estimates were refined. Even conservative calculations implied that more than a negligible fraction of the comet had disappeared. Without a resolved image of the original nucleus, astronomers relied on brightness to infer size and mass, but the shortfall persisted across reasonable assumptions. A body of ancient ice entered the solar system, warmed gently, split, and then lost material that could not be accounted for. Some researchers explored mechanical explanations that pushed against the boundaries of known comet behavior. One idea involved internal collapse rather than outward dispersal. In this scenario, voids or caverns within the nucleus might have compressed during separation, swallowing loose material instead of ejecting it. Collapses are known in terrestrial ice and have been suggested for some comets, but they still tend to produce external debris. No collapse is perfectly sealed. Yet, 3I Atlas behaved as though such perfection were possible. Others considered the presence of volatile substances uncommon in the solar system but potentially abundant elsewhere. Certain ices, such as supercooled carbon monoxide or nitrogen compounds, can undergo phase changes that produce little dust. If much of the nucleus consisted of such materials, the missing mass might have vaporized cleanly. Still, spectroscopy showed no convincing evidence of these compounds. Even faint signatures should have appeared. They did not. A more unsettling possibility remained. The missing mass might consist of material that interacts weakly with light, substances that scatter poorly, sublimate quietly, or dissipate rapidly without leaving observable traces. This idea did not require exotic physics, only unfamiliar chemistry. Interstellar objects form under different pressures, radiation fields, and histories. Their grains may possess unusual optical properties. Their structures may behave in ways that diverge from local expectations when heated. The more closely the missing mass was examined, the clearer it became that the issue lay not in the data, but in the assumptions used to interpret it. Another possibility was that the separation occurred earlier than first inferred. If the breakup happened far from the Sun, released material might have dispersed long before detection. By the time the fragments were recognized as separate, the debris could have thinned beyond detectability. Yet this idea conflicted with earlier observations. Previous images showed no elongation, no hint of doubling, no transitional phase. The shift from one body to two occurred too quickly to support a long, delayed separation. What remained was a persistent discomfort. A portion of the comet's substance had vanished in a way that defied established models. The missing mass became a symbol of how limited current understanding remains when confronted with interstellar geology. It reflected processes occurring far from Earth, shaped by environments humanity has not yet fully explored. This absence did more than puzzle observers. It set the stage for deeper speculation, pushing researchers to question whether materials formed in distant regions of the galaxy obey the same rules as those formed closer to home. If the mass did not escape violently, did not linger as dust, and left no trace in surrounding space, then perhaps the nature of the material itself was central to the mystery. Perhaps the galaxy contains substances that fracture without leaving evidence, materials that separate quietly, fading into space without announcing their departure. As the fragments of 3I Atlas continued on their path, they carried this implication with them. Part of the comet had slipped away, leaving behind only a gap in the data. At this stage, spectroscopy became the primary tool for further insight, not because it could reveal the mechanics of the breakup directly, but because it could map the comet's chemistry with exceptional sensitivity. If the fragmentation had been hidden, perhaps composition would offer indirect clues about the type of material capable of breaking without debris. Over many months, teams across the world collected spectra from both fragments, examining every accessible wavelength. At first glance, the results appeared familiar. Emissions from common volatile compounds were present. Faint cyanide features appeared. Carbon-bearing molecules were detected. The signatures of water ice turning into vapor were visible. This was expected. Interstellar comets form in protostellar disks, where the basic ingredients of ice and dust resemble those found in our own system. Yet beneath this familiarity lay subtle differences. One of the earliest stood out clearly. Water emission lines were weaker than expected. Comets approaching the inner solar system typically release large amounts of water vapor as they warm, producing strong spectral features. 3I Atlas did not. Its water output was low relative to its brightness, suggesting that water ice was either less abundant or less accessible near the surface. Instead, carbon monoxide and carbon dioxide played a larger role. These deeper frozen volatiles dominated the activity. Such elevated ratios point toward formation in an environment colder than any region where solar system comets are thought to originate, possibly near the outermost edges of a protoplanetary disk, or within a molecular cloud predating the Sun itself. This chemistry is not a minor detail. Such chemistry matters. A comet enriched with supervolatile materials and formed at extremely low temperatures may develop an internal structure unlike anything seen in solar system comets. Supervolatiles are substances that can change phase at very low temperatures. Even far from any star, they can migrate slowly through porous ice over millions of years. This gradual movement can reshape a nucleus from the inside, creating hardened layers, pockets of trapped gas, and crystalline arrangements that respond to heat in unexpected ways. If the nucleus of 3I Atlas contained such structures, its breakup may have followed pathways unfamiliar to standard comet models. Instead of fracturing along simple mechanical weaknesses, it may have separated along boundaries defined by chemical evolution, frozen into place over immense spans of time. This idea gained traction as researchers examined another clue: the striking weakness of dust-related spectral features. When comets shed particles, those grains reveal themselves in multiple ways. They scatter sunlight, but they also produce absorption and emission features linked to silicates and organic materials. In the case of 3I Atlas, these features were unusually faint. The dust signature was not just weak, it was far below expectations. This raised the possibility that the comet had an unusually low dust-to-ice ratio. Comets dominated by ice with very little embedded dust do exist, but they are rare. If this interstellar visitor were largely composed of ice, it could explain why fragmentation produced gas, but almost no solid debris. A dust-poor nucleus could split along icy plains that release volatiles while leaving behind little particulate matter. Still, faint dust signatures do not necessarily mean dust was absent. Another possibility was that the dust grains were distributed at extreme sizes. Very large grains, on the scale of millimeters or larger, scatter light inefficiently and can behave more like compact chunks that are difficult to detect unless solar radiation is intense. At the other extreme, extremely small grains, clusters measured in nanometers, interact with light in subtle ways. They can blend into the background of space, leaving none of the familiar spectral fingerprints associated with cometary dust. If the dust in 3I Atlas fell largely into one of these extremes, its breakup could have released particulate material that was effectively invisible. To investigate this, researchers turned to polarization measurements. Polarization studies can reveal information about particle size, shape, and alignment even when direct imaging fails. The results were surprising. Polarization signals were weak, far weaker than those observed in typical comets. This again pointed toward either a true scarcity of dust or grains with optical properties unlike those found in solar system bodies. The idea grew more compelling that interstellar processing had altered the comet's materials in fundamental ways. Long exposure to cosmic radiation can modify grain surfaces, making them less reflective, more transparent, or more irregular in structure. Another anomaly appeared in the infrared. Thermal emission from the coma was lower than expected, even after accounting for the comet's modest brightness. This suggested that any grains present were inefficient at absorbing and re-radiating heat. Some scientists proposed that the coma consisted largely of amorphous ice or extremely porous aggregates with very high void fractions. Materials like this can fracture and sublimate without producing fine dust. In laboratory studies, porous ice matrices have been observed to collapse quietly, leaving little residue. The resemblance to what was seen in 3I Atlas was difficult to ignore. Chemical analysis added another layer. Spectra revealed organic compounds, complex carbon chains, and fragments of prebiotic molecules. These substances are common in comets, but their abundance relative to the total volatile content was unusually high in this case. Such organics could occupy spaces between ice grains, acting as brittle binders or stiffening agents within the structure. If the interior contained radiation-hardened carbon networks or aromatic organic compounds, the mechanical behavior of the nucleus could differ sharply from that of typical comets. Solar system comets are thought to be held together largely by weak intermolecular forces between dust and ice. A structure reinforced by complex organics could fail in a more controlled and less chaotic manner. The composition thus painted a picture full of contradiction. Chemically, the comet shared many traits with ordinary icy bodies. Physically, it behaved as though governed by different rules. This combination led researchers toward a growing hypothesis. The comet formed in an environment with a very different balance of temperature, radiation, and pressure. one capable of producing ices with unusual mechanical properties, layered crystalline structures alternating with deposits of supervolatile compounds, could fracture under specific conditions without generating debris. Grain boundaries shaped by ancient cosmic ray exposure might act as planes of separation. Pressure pockets formed by slow volatile migration could vent silently during breakup, contributing to a clean division with no obvious signature. Spectroscopy, in this sense, became a guide rather than an answer. It pointed toward an origin far colder, far darker, and far older than any comet known to the solar system. It suggested a body shaped by quiet interstellar chemistry, refined over ages by radiation, reorganized by crystalline transitions, and altered in ways that current models barely address. The chemistry also hinted at something deeper. The breakup was not simply an accident of circumstance. It appeared to be a consequence of the comet's birth and long evolution. Its behavior was encoded in its molecular structure, written long before it encountered sunlight. Every missing dust feature, every understated emission line, every spectral silence suggested that the comet was predisposed to fracture differently, more like a geological body cleaving along a fault than an icy aggregate exploding apart. Spectroscopy did not solve the mystery. Instead, it ended the idea that surface processes alone could explain what had happened. It redirected attention inward, toward buried layers and long-term internal evolution. It opened the door to theories centered on silent fracture rather than violent disruption. As researchers followed these spectral clues, their focus shifted from what coated the comet's surface to what might have been unfolding deep inside. Spectra can describe outer composition, but they cannot reveal the hidden internal machinery that may have guided the breakup from within. If no debris was produced, then perhaps the fracture was not driven by external stress at all, but by internal processes. Pressure changes, crystallization, and slow thermal rearrangements may have been at work, processes that only prolonged interstellar isolation could produce. Interstellar comets are cold in a way nothing in the solar system truly experiences. They drift for millions or even billions of years through regions where background temperatures remain only a few degrees above absolute zero. In such environments, ice undergoes transformations unfamiliar to local bodies. Molecules freeze into amorphous states, rearrange under constant cosmic ray bombardment, and settle into metastable configurations balanced between rigidity and collapse. When sunlight finally warms these structures, their response can be unpredictable. Pressure may be released in slow, silent flows. Internal rearrangements may occur without reaching the surface. Cracks may form along crystalline planes with extraordinary precision. One particularly intriguing possibility involves the transition from amorphous ice to crystalline ice deep within the nucleus. Amorphous ice traps volatile molecules within its structure like sealed compartments. Over long timescales, cosmic rays can add to internal tension. When warmed beyond a critical temperature, amorphous ice reorganizes into a crystalline lattice, releasing trapped gases. If such a transition occurred deep inside 3I Atlas, it could generate internal pressure without producing surface dust. In typical comets, this pressure vents explosively, dragging material outward. But if the interior were highly porous or interconnected, the pressure might distribute evenly, softening the response. In this model, the nucleus would expand slightly, stretching along an internal boundary until it parted quietly. The separation would be clean, producing two stable fragments and little else. This matched the observations closely. Still, questions remained. Thermal models suggested that such transitions should occur over a range of depths, yet the inferred timing of the breakup appeared remarkably precise, as if the interior had reached a specific threshold. Another possibility involved sublimation pressure from deeply buried volatiles such as carbon monoxide or nitrogen. These substances can accumulate in pockets. Even slight warming causes them to expand. In most materials, this leads to explosive failure. But in substances subjected to extreme cold for long periods, pressure layers can form that hold evenly until the smallest disturbance triggers release. If such a pressure layer lay along a structural boundary, warming by the sun could have nudged it past a tipping point. Instead of erupting outward, the pressure may have escaped sideways, prying the nucleus apart, while leaving the surface largely intact. The internal rearrangement could have unfolded slowly, with only the final separation producing motion, gentle enough to avoid ejecting dust. Thermal conductivity differences offered another angle. Some interstellar bodies may contain layers with radically different abilities to conduct heat. Dense crusts may overlay fluffy interiors. Crystalline layers may alternate with porous deposits. Heat entering such a body does not spread evenly. It can concentrate along certain paths, creating zones of expansion next to zones of stability. In this scenario, 3I Atlas may have fractured through differential expansion. One region slowly swelled, while another resisted. Over time, stress built until separation occurred along the weakest boundary. If the expansion differences were small, the resulting fracture could be clean and nearly free of debris. The most radical ideas involved internal structures shaped by cosmic radiation. Over millions of years, radiation damage accumulates in interstellar ice. This can create microfractures, but it can also induce bonding between grains, forming a radiation-hardened matrix. Such a matrix might behave less like loose snow and more like brittle glass. Under the right conditions, glass-like materials fracture along smooth planes, producing clean separations rather than clouds of debris. If 3I Atlas developed such structures, its breakup could resemble geological cleavage. The nucleus could split along a radiation-shaped plane, leaving two smooth surfaces and almost no rubble. This would also explain the stability of the fragments, as brittle fracture imparts little rotational chaos. Yet, even the cleanest fractures on Earth produce some debris. Why had none been detected here? This question led researchers to consider reabsorption. If the fracture occurred deep inside, any dust generated might have been trapped within internal cavities instead of escaping into space. At this stage, the picture remained incomplete, but one conclusion was unavoidable. The breakup of 3I Atlas could not be understood through surface behavior alone. It demanded a view inward, toward internal structure shaped by interstellar history. The comet appeared to be a product of environments far removed from the solar system, carrying materials and architectures that fracture not with violence, but with quiet precision. In this framework, the fracture could have propagated outward without ever disturbing the comet's exterior. Any solid material released along the break would fall inward, slipping into internal voids rather than escaping into space. The nucleus would behave like a hollow shell, dividing into two parts, while the outer layers remained largely intact. Dust would stay trapped inside, sealed away from observation. This model is appealing in its simplicity, but it places strong demands on the comet's internal geometry. It would require large cavities aligned closely with planes of structural weakness. While voids are known to exist in icy bodies, such precise alignment is not common among solar system comets. Still, The unusual chemical signals detected in spectroscopy suggested that 3I Atlas may not share the same internal architecture as local examples. Interstellar evolution could plausibly sculpt interior landscapes far more complex than the loosely bound rubble piles typically inferred closer to the Sun. Other ideas followed. Some researchers proposed microscopic phase transitions within regions rich in organic material, where radiation-hardened carbon networks become brittle at certain temperatures. Others considered sublimation fronts that migrate inward instead of outward, or slow mechanical relaxation, where stress frozen into the nucleus during formation finally unwinds under sunlight. Across these different scenarios, one conclusion remained consistent. The split of 3I Atlas was not driven mainly by external forces. It was shaped from within by chemical, thermal, and structural histories, hidden beneath the surface and forged during its long passage through interstellar darkness. The comet's silent division became a reflection of unseen processes that govern matter in the cold spaces between stars. It suggested that interstellar geology may be more delicate and complex than previously assumed, shaped less by sudden violence and more by slow internal coordination. What telescopes recorded was only the final stage of a process that may have unfolded quietly over immense spans of time, encoded in layers of ice, pressure, and crystalline history, revealed only when sunlight warmed the nucleus enough to allow it to part. At this point, the mystery shifted. It no longer resided only in what astronomers could observe, but in everything they could not. Invisible fractures, unseen pressure gradients, and silent internal rearrangements appeared capable of producing a separation so precise that it left no trail behind. 3I Atlas suggested that some of the deepest forces in comet physics may lie not in solar heating or planetary tides, but in quiet transformations occurring inside frozen bodies that drift between stars. As investigators examined these internal mechanisms, a new question emerged with unsettling clarity. If the fragments separated cleanly and without debris, what served as the final trigger? It could not have been the familiar eruption of dust or the chaotic effects of surface sublimation. Attention turned instead toward processes driven not by solids, but by gas alone. In comet science, gas is usually the visible signal of activity. It forms the coma, shapes tails, and sculpts jets. As volatiles turn into vapor, they normally drag dust along, reshaping surfaces and announcing thermal stress through clear observational signatures. Yet there exists a narrower possibility, one far less familiar. Gas release without dust entrainment. Sublimation can, under very specific conditions, occur so cleanly and briefly that it expels almost no solid material at all. Such events are rarely observed because they require precise internal conditions. They may be common in the deep freeze of interstellar space, but uncommon in the solar system. Researchers began asking whether 3I Atlas could have been split by such invisible gas flows. To explore this idea, scientists revisited the physics of sublimation fronts, the internal boundaries where temperature and pressure cause ice to transition into vapor. In typical comets, these fronts move outward as the surface warms, but in bodies with unusual thermal properties, the front can also migrate inward, activating layers that have remained dormant for millions of years. When such a front encounters pockets of supervolatile material, such as carbon monoxide, nitrogen, or methane, it can trigger sudden, localized gas release. Imagine a sealed chamber within the nucleus, filled with volatile gas, accumulated over long timescales. As internal ice warms and reorganizes, the boundary weakens. A tiny crack forms, and gas escapes in a rapid pulse. The force involved may be small in absolute terms, but if it acts along a pre-existing internal weakness, it can be decisive. The nucleus can be pried apart without scattering dust, because the escaping molecules are too light to entrain solid particles. Gas jets of this kind are theoretically capable of producing the gentle separation speeds observed in 3I Atlas. They can push fragments apart without causing tumbling or chaotic motion. But for this explanation to hold, the gas flow must be both strong enough to overcome structural cohesion and clean enough to leave the surrounding coma undisturbed. To test this, researchers ran simulations of gas movement within porous bodies. The results were revealing. If porosity and grain size distribution were unusually uniform, as suggested by the comet's stable behavior, gas could travel through internal channels without erupting at the surface. It could migrate inward, collect along a weak plane, and then apply pressure evenly across that boundary. The breakup would resemble a controlled separation driven by distributed internal pressure rather than an explosion from the outside. Such a process would be nearly invisible. Gas escaping from within the fracture could disperse too quickly to leave a detectable signature. It might dissipate into vacuum before entering the coma, vanishing before even sensitive instruments could respond. Some researchers proposed an even more intriguing variation, known as coherent outgassing. In this scenario, gas is released not through a single vent or crack, but along an entire internal plane at once. Such an event would require exceptional conditions, uniform heating, evenly distributed volatiles, and a structural boundary ready to fail. If these factors aligned, the result would be a sheet-like release of gas, a sweeping breath that applies equal force across a broad surface. This curtain of gas could split the nucleus cleanly while leaving the outer layers largely intact. Coherent outgassing is rare in theory and has not been directly observed, but for an interstellar object with a highly homogeneous interior, a possibility hinted at by both spectral and dynamical evidence, it cannot be dismissed. Cosmic radiation could restructure materials into ordered patterns. Interstellar chemistry could produce layers of super-volatile compounds arranged with surprising regularity. If such symmetries existed, a symmetric release of gas becomes more plausible. Still, a key question remained. If invisible gas flows acted as the final agent of separation, why was no trace of the gas detected? The answer may lie in how quickly such gases disperse. Molecules like carbon monoxide and nitrogen can escape into vacuum at speeds far exceeding the escape velocity of a comet. When released suddenly, their density drops rapidly, falling below detection thresholds within seconds. In sunlight, they can ionize or dissociate almost immediately, leaving only a fleeting and narrow signal. It is also possible that the release occurred during a gap in observations between survey passes when no telescope was pointed at the comet. In that case, even a detectable event could have been missed, its molecular traces fading long before observations resumed. Yet this explanation remains unsatisfying on its own. For the separation to be as gentle and symmetrical as observed, the gas release must have been exquisitely balanced. Too strong, and the fragments would have accelerated apart. Too weak, and no separation would have occurred. The process would need to act like a precise instrument, applying just enough force along the right boundary. This led to a deeper idea. Perhaps the breakup was not driven by gas alone, but by a combination of internal restructuring and gas release. In this view, crystallization, pressure shifts, or thermal gradients slowly weakened the nucleus from within. Gas did not create the fracture. It exploited one that was already forming. The final step was not a violent eruption, but a gentle nudge, a brief release that tipped the structure past its threshold. Such a process would leave no obvious trace. It would be invisible not because it lacked power, but because it acted along a fault line shaped by millions of years of interstellar evolution, a whisper rather than a shout. This idea expanded the scope of comet physics. It suggested that a nucleus might be shaped not only by dust and ice, but by internal gas flows too subtle to observe directly, flows capable of rewriting expectations about fragmentation. In its silent division, 3I Atlas revealed the possibility of processes that act from within, hidden from sunlight and unmarked by debris. As the invisible winds hypothesis took its place among competing explanations, another question gained prominence. If neither dust nor violent jets nor catastrophic pressure surges were responsible, could the cause have come from outside the comet altogether? Gravity does not require debris. It leaves no plume. It can act silently, reshaping motion through differential pull. Tidal forces are known to tear bodies apart without impact. Yet in this case, the usual sources of tidal disruption were easily excluded. The comet never passed close to a planet. It did not approach the sun closely enough to experience strong tidal strain. Nothing in its immediate path appeared capable of exerting sufficient force, and yet the smooth divergence of the fragments, their symmetry, and their low separation speed hinted at a breakup driven by steady directional influence rather than internal violence. This prompted astronomers to look beyond familiar gravitational interactions. They began considering subtler influences, weaker or more diffuse than classical tides. The solar system contains complex gravitational structures, streams of dust, clusters of small bodies, gradients left behind by long-dissolved comets. These influences are normally negligible, but in rare circumstances, they might interact with fragile objects in unexpected ways. One possibility explored was interaction with unseen or poorly characterized mass concentrations, forces too weak to register directly, but capable of acting over time. While speculative, such ideas reflected the growing realization that the breakup of 3I Atlas could not be explained by any single familiar mechanism. Instead, it appeared to sit at the intersection of internal evolution and subtle external influence, a reminder that interstellar objects may respond to forces and processes that remain only partly understood. None of the proposed mechanisms fully accounted for one central feature of the event: the symmetry of the split. The fragments showed no signs of collision, no sudden change in direction, no sharp torque imparted at the moment of separation. Their paths after the breakup were smooth and orderly, free of jitter or disturbance. Whatever force divided them did so evenly, without favoring one side over the other. This led researchers to consider gravitational focusing, a class of effects involving very small accelerations caused by passing through regions of uneven mass distribution. In principle, if the comet had drifted through a faint but coherent gravitational gradient, perhaps created by an extended structure in the interplanetary medium, the wake of an ancient large comet, or a thin stream of dispersed matter, the nucleus might have experienced a slight but persistent differential pull across its length. Over time, such a gradient could accumulate stress within the interior, eventually leading to a silent fracture. The appeal of this idea lay in its elegance. It could explain the gentle motion of the fragments, the lack of debris, and the symmetry of their behavior. However, it also demanded the existence of a structure so diffuse and subtle that it left no trace detectable by modern instruments. No such mass distribution is known, and no indirect evidence points to its presence. While interstellar space contains filaments of gas and dust, the interior of the solar system is far too sparse for such gradients to build up to meaningful levels. Attention then shifted to the comet's long journey before entering the solar system. For countless ages, 3I Atlas traveled through interstellar space, where encounters with passing stars, molecular clouds, or other massive objects could have imposed tidal stresses on its structure. Even distant stellar flybys can stretch small bodies, imprinting internal strains that remain locked in place for millions of years. These stresses do not necessarily break an object immediately. Instead, they can persist, dormant, awaiting a final trigger. In this scenario, the Sun played only a minor role. It did not cause the breakup directly. It merely completed a process that began long ago, when the comet passed near another star and experienced a differential pull strong enough to prime a structural plane within its interior. Over time, the nucleus may have partially relaxed, but never fully healed. When solar warmth softened the ice just enough that ancient stress line reopened, this idea explained the cleanliness of the break. The fracture was old, sharply defined, and deeply embedded. At the moment of separation, no fresh tearing occurred. Frozen materials along the fault simply gave way. No debris needed to be produced, because the structure had already been divided in all but name. This interpretation aligned with emerging views of interstellar comets as archives of ancient encounters, bodies that store the mechanical memory of environments far removed from the solar system. Yet even this explanation left one crucial question unanswered. Why did the fragments separate so gently? A stress fracture may initiate a split, but it does not determine how fast the pieces move apart. Something else must have guided their motion after separation. To address this, astronomers examined more subtle influences, especially the combined effects of gravity and radiation. Radiation pressure, the push exerted by sunlight, is usually important only for dust grains, not kilometer-scale bodies. But if a nucleus is already weakened along a plane, even tiny differences in exposed surface area between two halves can matter. Once separated, solar radiation could act like a steady breeze, nudging the fragments apart slowly and evenly. In this model, the Sun did not split the comet. It merely encouraged the drift after the split had begun. The absence of debris, the quiet nature of the event, and the low separation speed all fit this picture. The nucleus, already primed by ancient stresses, parted when warmed. Radiation pressure then provided the gentle push that carried the fragments apart. Planetary gravity entered the discussion as well. As the comet moved deeper into the solar system, it passed through regions influenced by the gravity of large planets. These forces are weak at great distances, but they act continuously. Jupiter, in particular, exerts a broad gravitational influence. While not strong enough to tear a comet apart directly, its persistent pull can subtly distort trajectories. If the nucleus was already near failure, even tiny differential accelerations, measured in fractions of a millimeter per second squared, could have been enough to tip the balance. In this view, ancient interstellar stress, mild solar heating, radiation pressure, and planetary gravity all worked together. None acted alone as a destroyer. Instead, they formed a coordinated system of gentle influences that guided a fracture whose origin lay deep in the comet's past. As scientists weighed these possibilities, a broader conclusion began to take shape. Gravity, in all its quiet forms, may have acted not as a blunt force, but as a sculptor. It did not tear the comet violently apart, It guided an unbinding, already encoded in the nucleus, shaping a division that left no plume, no trail, no visible scar beyond the separation itself. This view reframed the breakup of 3I Atlas as part of a larger narrative, a narrative in which forces so faint they leave no wake can still align perfectly with pre-existing weaknesses, carving a silent division through a body shaped by interstellar drift. A comet split by whispering forces, not roaring ones. A fracture written by geometry and history rather than chaos. Rotation then entered the investigation, not as an obvious suspect, but as a quiet and persistent influence. For most solar system comets, rotational breakup is dramatic. As sunlight drives uneven sublimation, jets form and apply torque. The nucleus spins faster and faster until centrifugal forces overwhelm its strength. When failure comes, it is violent. Pieces fly apart, dust erupts, trails appear. None of this was seen in 3I Atlas, and yet, rotation in its gentlest form may still have played a role. To explore this, researchers revisited the light curves recorded before and after the breakup. Light curves often reveal rotation through periodic brightening and dimming as an irregular body spins. In this case, the signal was faint but present. It suggested slow, steady rotation. Importantly, the rotation appeared stable. There was no sign of rapid spin-up, no erratic modulation, no indication that the nucleus was tearing itself apart through centrifugal stress. The comet spun calmly, maintaining its momentum without instability. This ruled out rotational overload as the primary cause, but it did not rule out rotation as a contributing factor. Instead, rotation may have shaped how stresses were distributed inside the nucleus. One hypothesis focused on spin axis orientation. A slowly rotating comet with its spin axis pointed toward the sun experiences uneven heating. One pole warms, while the opposite remains cold. This creates temperature gradients that extend into the interior. If the nucleus contains pre-existing planes of weakness, such gradients can concentrate stress along those planes. In this scenario, rotation did not cause the breakup. It guided it. The slow spin moderated how thermal expansion acted across the nucleus, nudging internal stresses toward a particular boundary. As sunlight penetrated deeper layers, expanding ice along that plane, rotation gently pulled the structure toward separation. The process was gradual, controlled, and quiet, more like an unzipping than a tear. Clues supporting this idea came from the behavior of the fragments after separation. If rotation had played a disruptive role, the fragments would likely show signs of inherited chaos, different spin rates, tumbling motion, or unstable light curves. Instead, both fragments appeared calm. Their rotation was slow and steady, with little deviation. This suggested that angular momentum had been shared evenly. Such balance is rare in violent breakups. When comets fail under rotational stress, fragments typically inherit very different spin states. But in a gentle, quasi-static separation, angular momentum can be divided smoothly, leaving both pieces rotating in similar ways. Models of such gentle separations showed that if a nucleus has strong internal symmetry, whether geometric or compositional, rotation can encourage a split along that symmetry plane. The required force is small. Even modest thermal expansion can trigger separation if rotation has been quietly biasing the structure for long periods. This led some researchers to consider whether 3I Atlas had experienced spin-induced stress over millions of years. Even slow rotation can influence internal structure over long timescales. Centrifugal forces, though weak, can affect grain alignment, void geometry, and the distribution of microcracks. Over time, these effects can create preferred directions of weakness. In this view, the breakup was not a sudden reaction to solar heating. It was the culmination of a long internal evolution. Rotation shaped the nucleus slowly, and sunlight merely revealed what was already prepared. One final possibility brought these ideas together. Many comets exhibit bilobed shapes, two larger masses connected by a narrow neck. If 3I Atlas formed this way, or evolved into such a configuration during its interstellar journey, the neck would be a natural point of failure. Slow rotation can keep such bodies stable for long periods, but even small changes in temperature or composition can weaken the connection. If the nucleus consisted of two lobes joined by a fragile bridge, the breakup would require little force. The neck could separate quietly, producing two stable fragments with minimal debris. This scenario naturally explains the symmetry of the split, the low separation velocity, and the calm behavior of the fragments. In this light, the silent division of 3I Atlas may not represent a single dramatic event, but the gentle resolution of a structure shaped long ago, a body formed, stressed, and sculpted in interstellar space, finally parting when conditions aligned just enough to let it do so without noise. When this configuration occurs, the two lobes can drift apart gently, each carrying a share of the angular momentum they inherited from the original body. This model accounted for several puzzling observations at once. It explained the clean separation, the near absence of debris, the stable rotation of the fragments, and the remarkable symmetry in their motion. It suggested that 3I Atlas may not have become two objects through a sudden act of destruction, but rather returned to a natural duality that had existed beneath the surface for a very long time. In this view, the breakup did not create something new. It revealed what had already been there, shaped slowly by rotation during an endless journey through interstellar space. Yet even this explanation could not fully resolve the most troubling detail. Rubble pile comets, when they split, almost always shed material from the narrow neck that once held them together. Dust, grains, and small fragments escape easily from such regions. The pristine divide seen in 3I Atlas implied that if a neck existed, it was composed of material capable of breaking with extraordinary precision, without scattering particulate matter. This pointed once again toward an unusual composition. Ices hardened by cosmic radiation, crystalline structures reinforced over immense spans of time, or materials far more cohesive than those found in local comets, may have played a role. Rotation therefore returned to the narrative, not as a dramatic trigger, but as a quiet architect. It was an influence that shaped the comet's interior over millions of years, aligning weaknesses, guiding stresses, and preparing the conditions for a separation so delicate that it left no visible trace. Rotation did not shout. It murmured, working patiently in the darkness between stars. It may have provided the final piece needed to understand how 3I Atlas accomplished something that seemed impossible, dividing itself with controlled grace, leaving behind only two fragments moving in silent synchrony. As astronomers worked through and eliminated familiar explanations, thermal cracking, sublimation-driven jets, rotational overload, and obvious gravitational tides, one idea began to stand out more clearly. It had been present since the moment the object received its designation as the third known interstellar visitor observed passing through the solar system. Unlike comets native to the Oort cloud or the Kuiper belt, Interstellar objects carry the imprint of distant birthplaces, shaped by environments that may differ fundamentally from those around the Sun. Their histories are long. Their journeys span unimaginable distances. Their past encounters are largely unknowable. In the case of 3I Atlas, the idea of an unfamiliar origin offered strong explanatory power. Studying a comet formed near the Sun means studying matter shaped by a familiar radiation environment, familiar temperature ranges, and a chemical inventory similar to that which contributed to the formation of Earth. Confronting an interstellar comet is different. It means examining material forged under alien conditions, altered by temperatures never experienced in the solar system, by cosmic ray intensities far beyond local norms, and by encounters with stars or massive bodies that reshaped it grain by grain. 3I Atlas behaved exactly like such a traveler. Its lack of debris, its immaculate split, its subdued coma, and its symmetry all pointed toward a body whose internal structure and chemistry followed rules not yet well represented in comet science. One of the earliest clues lay in its abundance of supervolatiles. Measurements showed that the ratios of carbon monoxide and carbon dioxide to water were higher than those found in most solar system comets. This suggested formation in an environment far colder than the regions where typical comet nuclei emerge. Such conditions could exist at the extreme outer edge of a protoplanetary disk, where temperatures remain low enough for exotic ices to accumulate. They could also exist deeper still, within a molecular cloud that gave rise to the comet's parent star, where temperatures hover just a few degrees above absolute zero. In these environments, ice forms differently. Water does not always crystallize in uniform ways. Organic molecules can integrate into ice matrices, strengthening their mechanical properties. Carbon monoxide can freeze into layers that are brittle yet cohesive, unlike anything commonly found in local comets. These exotic ices, layered and interwoven through the nucleus, could establish fracture planes so clean that a breakup would produce gas without visible debris. But chemistry alone was not the whole story. Interstellar comets also endure cosmic radiation for far longer than their solar system counterparts. Comets native to the Sun experience radiation filtered by the heliosphere, occasional energetic events, and limited exposure times. Interstellar objects travel unshielded through the galaxy, subject to cosmic rays whose intensity and character vary widely. These high-energy particles penetrate deeply into icy bodies. Over millions of years, they alter molecular bonds, rearrange crystalline structures, and create internal defects. The result can be a complex interior composed of radiation-hardened layers, brittle zones, and highly porous regions. Such an interior bears little resemblance to the loosely aggregated material inferred in comets that have always lived under the Sun's magnetic protection. The longer 3I Atlas drifted through interstellar space, the more its interior likely evolved. Radiation may have annealed some layers, turning weakly bound grains into more rigid crystalline sheets. At the same time, it may have carved voids or microfractures elsewhere. Over immense spans of time, these opposing processes could sculpt a nucleus that was both fragile and precise, predisposed to split cleanly along defined planes without scattering debris. Its orbit added further context. The comet may have been ejected from its home system through a close encounter with a massive object, such as a gas giant, a companion star, or a passing stellar neighbor. Such interactions can imprint tidal stresses that deform small bodies internally. These stresses can freeze into the structure, forming fault lines that persist long after the encounter has passed. If 3I Atlas carried such an ancient scar, then the Sun did not create its breakup, it revealed it. Mild solar heating may have softened the ice just enough to allow a pre-existing weakness to open. The separation would then appear clean and controlled, because the fracture had already been prepared long ago. The possibility that the comet originated in a binary star system strengthened this picture. Binary systems create complex gravitational environments. Comets formed within them may experience repeated tidal stresses and dramatic temperature variations. These conditions can produce layered internal structures unmatched by any solar system example. Such origins could also explain the comet's apparent lack of dust. If 3I Atlas formed in a region with low metallicity, where heavy elements were scarce, its dust-to-ice ratio would naturally be low. A body dominated by ice and organic material, with few solid grains, would produce gas during breakup, but almost no particulate matter. This aligns closely with what was observed. Time itself also matters. Interstellar comets may be far older than most solar system comets. Over hundreds of millions of years, ices can slowly fuse under faint thermal gradients. Organic compounds can polymerize into long, stiff chains. Micropores can collapse, redistributing mass internally. These processes can make a nucleus either more brittle or more cohesive, depending on composition. Either outcome could support an immaculate split when stress is applied along the right plane. Seen this way, the breakup of 3I Atlas does not violate physics. It reflects physics operating under conditions rarely encountered near the Sun. Every oddity, every absence of dust, every sign of symmetry points to an object shaped by a galactic journey. The diversity of the galaxy extends not only to stars and planets, but to the smallest icy wanderers drifting between them. When such an object enters the solar system, it brings with it the imprint of environments entirely foreign to Earth. The question of why 3I Atlas split without fragment trails takes on a different meaning. The comet may simply not have been capable of breaking in the way local comets do. Its materials, its internal architecture, its radiation history, and the stresses of ejection from a distant system may have combined to create a nucleus predisposed to divide cleanly. What appeared anomalous may have been inevitable for a body shaped in the cold depths of another star's cradle. It was not just a comet that broke silently. It was an emissary from elsewhere, following rules written in a different corner of the galaxy, carrying within its fracture the quiet signature of its interstellar origin. By the time the fragments of 3I Atlas had drifted far enough apart to develop independent comae, the scientific community had already mobilized a broad network of instruments to study the event. The comet itself was receding, moving slowly away from the Sun, growing fainter with each passing night. Yet the questions it raised became sharper, not weaker. A split without dust, without debris, without spectacle demanded explanation. Ground-based telescopes equipped with wide-field images formed the first line of investigation. These instruments, sensitive to subtle brightness changes, were used to reconstruct the breakup by comparing archival images with the newly diverging fragment paths. Astronomers searched data from surveys such as Atlas, Pan-STARRS, and others that had scanned the region near the inferred time of separation. Automated systems flagged potential anomalies, while human analysts examined the images by eye, looking for hints algorithms might miss. Researchers hoped to find the earliest signs of elongation, a faint suggestion that the comet's light profile had begun to split. Even with advanced image subtraction and deep stacking techniques, nothing definitive emerged. There were no transition frames, no blurred doubling, no faint dust haze preceding the discovery. The breakup remained hidden within unavoidable observational gaps, moments when telescopes were pointed elsewhere or conditions prevented observation. This absence only deepened the mystery. The most important event in the comet's recent history had occurred silently and invisibly. With imaging exhausted, scientists turned again to spectroscopy. Large telescopes in locations such as Chile, Hawaii, and the Canary Islands gathered spectra across ultraviolet, visible, and infrared wavelengths. These observations continued long after the comet had faded, pushing detectors close to their sensitivity limits. Researchers built detailed models of sublimation rates, volatile composition, and thermal evolution. Comparing the fragment's behavior with that of known comets, they simulated how freshly exposed surfaces should respond after a breakup, predicting surges in gas release and changes in spectral lines. Yet nothing matched. The fragments remained quiet. Their chemical signatures stayed steady, even as new regions rotated into sunlight. No bursts of activity appeared. The coma around each fragment stayed narrow and restrained. If new surfaces had been created, they behaved with remarkable discipline. Unable to extract answers from ground-based observations alone, astronomers turned to space-based instruments. Telescopes above Earth's atmosphere offered access to thermal and ultraviolet signals free from atmospheric interference. These instruments revealed subtle temperature variations, small changes in reflectivity, and gentle thermal gradients across the fragments. The data were precise, but they reinforced the same conclusion. 3I Atlas was not behaving like any comet previously studied. Its breakup had been quiet by design, shaped by an internal history that science was only beginning to glimpse. Even with access to space-based instruments, the comet continued to resist simple explanation. Thermal imaging revealed no localized regions of unusually warm ice where fresh fracture surfaces were expected to appear. There were no hotspots tracing a newly exposed interior. Instead, temperature maps across both fragments were smooth and continuous, indistinguishable from those of long-exposed surfaces. The fragments behaved thermally as though they had always existed independently, not as though they had just been torn apart. This posed a direct contradiction to standard expectations. For a breakup to occur, material must separate. Separation creates new surfaces. New surfaces, in turn, should respond differently to sunlight, warming more quickly, cooling at different rates, and sublimating unevenly. These differences are normally among the clearest indicators of fragmentation. Yet, in the case of 3I Atlas, none of these signatures appeared. If new planes of division existed, they behaved exactly like older terrain, with no measurable thermal or chemical distinction. Faced with this inconsistency, researchers shifted toward large-scale numerical modeling. Using high-performance computing systems, teams simulated a wide range of internal structures and compositions to see which scenarios could reproduce the observations. They varied grain size distributions, porosity levels, volatile concentrations, crystalline alignments, radiation-processed layers, and internal void networks. Models tested both cohesive monoliths and loosely bound rubble piles. Some assumed bilobed geometries, others near spherical symmetry. Some included exotic ices formed under deep interstellar cold, while others explored unexpected internal temperature gradients. After thousands of simulation runs, only a small subset produced outcomes resembling what was observed. Slow, silent separations with minimal debris and stable fragment motion. These successful cases required highly specific conditions. The nucleus had to possess uniformly distributed microcrystalline structures, a deeply embedded but coherent plane of weakness, a porosity profile that allowed internal pressure to diffuse without eruption, and a thermal environment capable of maintaining near equilibrium across both emerging fragments. Such a configuration would be extremely unlikely for a comet formed and evolved entirely within the solar system. For an object shaped over millions of years in interstellar space, however, it became more plausible. As simulations narrowed the range of viable explanations, attention turned to the future. If current observations could not fully resolve the mystery, perhaps upcoming tools could. Although the James Webb Space Telescope was not positioned to observe 3I Atlas directly, its studies of other faint icy bodies proved valuable. Webb's detailed spectroscopy of distant ices under solar heating conditions helped researchers refine models of how exotic volatiles behave, how they store energy, and how they restructure over long timescales. These analog studies offered indirect insight into what might be happening inside interstellar comets. At the same time, planetary scientists began outlining mission concepts aimed at future interstellar visitors. Interest in such missions grew after the passage of the first known interstellar object and intensified further following the strange behavior of 3I Atlas. Proposed designs included rapid response probes capable of achieving very high velocities, equipped with dust collectors, volatile analyzers, impact sensors, and compact landers. The goal was straightforward. If another interstellar comet were to fragment, scientists wanted to observe the event directly, close enough to detect even the faintest release of material. Parallel efforts focused on improving observational strategies from Earth. Survey cadence was re-evaluated. Sky coverage was expanded. Automated detection algorithms were refined to flag subtle changes in morphology and motion more quickly. The challenge was not only to discover interstellar objects earlier, but to monitor them continuously enough to avoid missing critical moments. The silent fracture of 3I Atlas had made clear how much information can be lost in even brief observational gaps. Despite these advances, the mystery itself remained unresolved. Observations and models increasingly suggested that the phenomenon was rooted in interstellar chemistry and deep cold physics, in microstructures formed long before the comet entered the sun's influence. Modern instruments had revealed the comet's behavior with remarkable precision, but they had not uncovered a definitive cause. Instead, they outlined the boundaries of current understanding and hinted at where established cometary physics might need to expand. As the fragments continued outward, they grew steadily fainter, retreating from the region where detailed observation was possible. Yet scientific interest did not fade with their light. Instead, it broadened. The event became part of a larger effort to prepare for future encounters with material from beyond the solar system. Researchers recognized that interstellar objects may not simply extend known categories of comets, but represent fundamentally different classes of matter, shaped by unfamiliar histories. Across the months of observation, from the comet's initial detection to the slow separation of its twin fragments, one feature remained constant: the empty space where debris should have been. No dust cloud formed, no trail marked the rupture. The region between the fragments stayed clean and undisturbed. This absence became as informative as any detected signal. The fragments themselves continued on calm, stable trajectories. They did not crumble further. They did not erupt with delayed activity. They did not show signs of increasing rotational stress. Instead, each maintained a steady, restrained level of sublimation, as though the breakup had released them into a more stable state, rather than a more fragile one. This behavior challenged long-held assumptions about fragility. Comets are typically considered archetypes of impermanence, porous bodies that fail easily. Yet this interstellar visitor demonstrated a different kind of vulnerability, one that allowed for quiet transformation rather than violent destruction. This forced a reconsideration of what fragility means in the context of interstellar matter. Objects shaped far from the sun may not fail through explosive processes. Instead, they may undergo internal reorganization, separating along prepared boundaries without chaos. Their weakness may lie not in their inability to hold together, but in their tendency to part gracefully when conditions align. The silence of the breakup carried a broader implication. Not all cosmic processes announce themselves through brightness, dust, or motion. Some unfold through forces too subtle, too cold, or too evenly distributed to produce obvious signatures. Just as gravity shapes orbits without collisions, and radiation reshapes molecules without visible scars, large-scale transformations can occur without spectacle. In this sense, 3I Atlas highlighted the limits of human perception. Astronomers rely on light, spectra, dust, and motion, signals that instruments are designed to detect. Yet the universe contains processes that leave little or no trace in these channels. The comet's silent division suggested that entire categories of behavior may remain largely invisible, not because they are rare, but because they do not interact strongly with the signals we expect. As an interstellar visitor, 3I Atlas became a reminder that the galaxy is filled with material shaped by histories we have not observed and conditions we cannot yet reproduce. Each such object carries information encoded not only in what it reveals, but in what it withholds. Its breakup, without a fragment trail, challenged the assumption that all fractures must announce themselves. It showed that absence itself can be a form of evidence, pointing toward internal architectures governed by different rules. As the fragments faded into the darkness beyond the sun's reach, the comet's physical presence diminished, but its scientific impact persisted. The instruments that once tracked its faint glow turned to other targets, and the sky returned to its steady pattern of distant stars. Yet the questions raised by this object remained active, shaping future research and observation strategies. The story of 3I Atlas did not conclude with a definitive answer. Instead, it settled into a quieter state, becoming part of a growing framework for understanding interstellar matter. Its fragments continued their journey, moving back into the deep cold, where sunlight thins and interstellar processes resume control. Somewhere far from Earth, they will drift past other stars and clouds, carrying with them the structural memory of their formation and separation. For now, what remains is a refined awareness that some of the most important processes in the universe operate without noise or debris. The silent fracture of 3I Atlas serves as a marker, not of failure, but of complexity. It reminds us that understanding often advances not through dramatic signals, but through careful attention to what is missing. In that recognition lies the foundation for the next step forward. As science prepares for future encounters with visitors shaped by other suns, other histories, and other rules,